When working in EnerCalc 3D, there are many times where we want to apply an area load, like a uniformly distributed load, over a specific area in a model to ultimately get that load to the members in that area. We have a tool that's specifically for that purpose. It's called area loads, and we'll take a look at how to use that in just a second. Before we do that, I'd just like to come in and show that I've predefined some load cases in this model so that I have some cases to insert these new load items into. In order to use the area loads tool, I'll just click on draw loads and then come down to area loads. The area load dialog reminds us that the purpose of the tool ultimately is to get load applied to members, not to plates. The load case drop down allows me to specify which case I want to contain the new load. And then I can define the load by saying that I want to specify it with respect to either the local or the global coordinate axis system. And then I can choose the direction. So if I want to represent a gravity load, I could say global y-axis, and then I'll use a negative magnitude. Maybe we'll apply a negative 30 pounds per square foot. This distribution drop-down lists a variety of options that the program can use to distribute an area load to the bounding members within the area. I won't go through an explanation of what each of these does, but just know that the explanation is in the documents, and there's some good illustrations of the effects of choosing these different types of distributions. I'll choose the two-way rectangular subareas option, and we'll see what that means in a minute. The node at the bottom reminds us that we need to pick 4 nodes to define the area after we click the apply button. So I'll click apply, and then with the pen cursor, I'll just work my way around the perimeter of the area that I want to have loaded. And when I click that 4th node, we see a graphic that shows that we've applied an area load, and it confirms the magnitude and direction, and it reminds us that we use the two-way rectangular subareas method. While the pen is still active, I will also just come back in here and click 4 more nodes in a sub area to show that area loads can be superimposed. So we have 30 applied on the entire area, and then an additional 30 applied just in this bay, and we'll see that in a few minutes as well. Now I can come to the Tables tab and then over to Area Loads, and when the dead load case is selected, I can see the 2 area loads that I've defined. I can see the nodes that have been defined as the corners or the vertices of the areas. I can see that they both used the global coordinate axis system, and they've both been applied in the global y direction. They use the rectangular subareas method, the two-way distribution, and they both have a magnitude of negative 30. What we could also do is just use this to show that we can change these things by saying OK, and then we see an update here. Now, the area loads are really convenient because they keep one concise definition for a load in a location that can be defined as easily as we just changed 30 to 60, and it affects many members all at one time. So there's good reason to use area loads, and they're very convenient. They also offer another option which removes a little bit of the concise behavior of the area load itself, but it makes things more granular and easier for us to modify if we have specific things that we want to modify in particular locations. And that is this option down here that says to convert the current case to line loads. Corresponding option here converts all cases to line loads. But what we'll do is click the Convert Current Case to Line Loads button. And now we can see that instead of the area load graphic, we see a line load depiction of what those area loads were actually doing to all those members. And now we can start to understand this two-way distribution a little bit better. We can visualize that it was drawing angle bisectors until they met. And in that area, in those corners, it was doing triangular or linear varying distributions. Once those bisectors met, then it was doing a uniform distribution where half goes to one beam and half goes to the other, and so on. The other thing that this shows us more clearly is that there definitely are a couple of loads stacked over here in this third bay because of the second load that we applied. So the ability to come in and take a look at these things in the form of line loads is convenient in the sense that we can open the line loads table and then come right into the selected member, right to the particular load of interest, and we could modify these if we wanted to. Notice that these are defining, again, the coordinate axis system and the direction, the starting value and the ending value, and then the locations along the member length, starting at the start and measuring toward the ending. And so once we explode these loads into line loads, they're much more granular, they're easy to come in and modify, we have much more control over things, but the important thing to remember is that if we come back to the area loads table, they're now gone because they're either one or the other, they're not both. So now we don't have that nice concise format, instead we have the much more granular format. So area loads can be very useful and powerful on your models, and just keep this option in mind and remember the effects and the pros and cons of keeping them as area loads versus changing them to individual line loads where you can see things in a much more granular format.